Howdy, and welcome to Chapter 18. We're moving along in our book, and this chapter is on secure software development. By now, you should have reviewed the OWASP Top 10 list. We're going to be moving into more soft topics after this topic. So let's look ahead. We've got business continuity and disaster recovery, risk management, change management, incident response. We may or may not do computer forensics or touch it lightly. Legal issue and ethics, and privacy. So this is the last of our really technical, hey, I'm a software programmer, or I need to know how this works. If you are truly interested in secure software development, you need to take a course in it. We still do not architect and engineer security in our design. Security is an afterthought in many cases, not all cases, in many cases. If you were in my law and policy class, we would be talking about a new law in the EU, General Data Protection Regulation, and one of the aspects of that law is security and privacy is required in the design of any system. So, next slide. As someone who teaches intellectual property and am a licensed patent attorney, I respect the IP of others, so as always, I want to give credit where credit is due to my good friend at the University of Houston, Dr. Art Conklin, who has given me permission to use these slides. Good guy. I think he's done an excellent job in this textbook. I hope you agree. So, video 1, secure software development. The learning objectives is I want you to think about how secure coding can be incorporated into the software development process. Do you need to be a programmer? No. But we have a software development process. We have a software lifecycle, or we should, where you create software. Perhaps you do it by a number of ways. The old-fashioned way was the waterfall method. Now we go to evolving prototypes, agile prototypes. There's a whole bunch of names for basically the same concept that says you build and test as you go, build, test, and put into operation as you go, as opposed to the old waterfall method that said you build it, you test it, and then you put it into operation. It was for a different class of machines in a different time. You need to know major types of coding areas and their root causes. Don't forget you've got the OWASP Top 10, which according to the syllabus, by this time you should have reviewed. You want to describe good software development practices and how using a software development process enforces security. And you need to know how an application of hardening techniques. Now again, this is a different audience for this class, so I'm not going to hold you to showing you some code and asking you what the problem is. I just want you to know the process. Let's go through the definitions. An agile model is a software development model, or mode rather, software development mode, built around the idea of many small iterations. So it's agile. They continually yield a finished product at the completion of each iteration. This is not only a software or technical techniques, this is a marketing technique. In the old days, you used to take your system requirements, come up with your specification. You'd go off anywhere from 2 months to 2 years to develop a product. Then you'd put out in the marketplace and find out it wasn't what the customer wanted. So Agile is the best of both worlds in both business and engineering. We're going to put some requirements in, not all. We're going to have a limited product. Is this what you want? And at the same time, we can stage the testing and security. Black box testing is a form of testing in software engineering where the tester has no knowledge of the inner workings of a mechanism. I throw it to the black box testing, and I don't know how it works. It comes out, probably checks input-output constraints, probably tries some buffer overflow, probably tries some things, but I don't know. Buffer overflow is a very typical, a specific time of software coding, but a typical one that enables user input to overflow the allocated storage area and corrupt a running program. It gets into an area of memory not properly allocated to that. Always on the OWASP Top 10. The canonicalization error arises from the fact that inputs to a web application may be processed by multiple applications, such as a web server, application server, database server, each with its own parsers, to resolve appropriate issues. So, not going to go into that much, just be aware of the term. Code injection, again, is in OWASP, I believe it's number 1, top 10. An attack where unauthorized executable code is injected via an interface in an attempt to get it to run on a system. CVE, you need to know these terms. Common vulnerabilities and exposure is a structured language XML schema used to describe known vulnerabilities in software. And the common weakness enumeration is a structured language, again an XML schema, used to describe known weakness patterns in software that can result in vulnerabilities. If you are serious about cybersecurity, CVE, CWE, this needs to be part of your common everyday toolkit, knowing and understanding that. Cryptographically random is a random number that is derived from a non-deterministic source. Thus, knowing one random number provides no insight into the next. So it's truly random. The CWE SANS Top 20 Most Dangerous Software Errors is a list maintained by SANS and MITRE that includes the 25 most dangerous programming errors categorized in 3 distinct areas. Now, I gave you the OWASP Top 10 on your own, and we will add this to one of the videos. I want you to look at the SANS Top 25. Again, think about this. This is all free information. Somebody's done the hard work, and you're going to benefit from it. If you keep up with OWASP, if you keep up with SANS, the Common Vulnerability Database, if you keep up with all that, someone else has done the work. Deprecated function is a function that has been superseded and or no longer fit for use. Evolutionary model is an iterative model designed to enable the construction of increasingly complex versions of a project. Fuzzing, I love fuzzing. It's the use of large quantities of data to test and interface against security vulnerabilities, also known as fuzzy testing. It's going to throw, what fuzzy testing in its purest form is throw any kind of file and see what happens. Okay, so large quantities of data, test the interface, also way different kinds of data. So you have an application expecting financial transactions, and you throw it a file that doesn't even make sense, a data file that doesn't even make sense, just to see how the system's going to react. Because sometimes, of course, it's going to result in an unpredictable consequence, but you want to have an idea of how unpredictable that consequence is. Gray box testing is a form of testing where the tester has limited or partial knowledge of the inner workings of a system. These should be all terms, if you're a computer science majors, that you're going to go through software engineering. All right, least privilege, review. It's a security principle in which a user is provided with a minimum set of rights and privileges that he or she needs to perform required functions. The goal is to limit the potential damage that any user can cause. Requirements phase. This phase should define the specific security requirements if there is any expectation of them being designed into the project. Okay, your SDL model, your secure development lifecycle, is a process model to ensure security functions consideration in each part of the build process or software in an effort to reduce attack surfaces and vulnerabilities. The spiral model. This is a design model that has steps in a process that execute in a spiral fashion, repeating at different levels with such revolution of the model. SQL injection is a form of injection, right? An attack against a SQL engine parser designed to perform unauthorized database activities. Testing phase, guess what? It's the final phase in the process where testing is done before the product is given to end users. Testing is its own domain. We've seen fuzzy testing, we've seen all this other thing. Testing many times is an afterthought. Hey, we're down to the wire. We're at the schedule. Just run the stuff and see if it works. This is one good thing about the iterative model, whether you call it spiral, evolving, whatever. You need to be testing operationally, not just testing looking for bugs, not verification. Verification is where you verify that the code does what you think needs to be done. Validation is, was it the code you wanted for that purpose? So testing phase gets to be left at the end. We're out of time, we're out of money. Sometimes it's an ethical issue. One of the ones that was brought to me recently was a manager said to sign off on some testing, and the programmers hypothetically would be like, but we haven't done it. What do I do? Okay. Top 25 list, SANS and MITRE, 25 most dangerous programming. Use case. This is a review process that can understand the requirements of a piece of software. The review process use cases is tell me in words how this is going to be used. Don't tell me what the technology is. Don't tell me what the benefits are in technical terms. Tell me how I'm going to use it. Tell me how I'm going to interact it. These are the use cases. Waterfall model, yay. If you're an old timer like me, it's a multi-step process in which the steps follow each other in a linear, one-way fashion, like water over waterfall. For those of you who are in the military, going in the military, DoD 2167 standard was the old waterfall model. I have not developed software for the military for probably about 15 years, so I don't know if it's still in use. I would guess somewhere it is. White box testing, and by the way, waterfall model, I'm talking about it from DoD. It was widespread through software engineering. White box testing is a testing methodology where the test team has access to the design and coding elements, as opposed to back box. And 0 day is a name given to a vulnerability whose existence is known, but not to the development of the software. Hence, it will be exploited before patches are developed and released. Okay, let's talk about the software engineering process. You know, software doesn't build itself. A little side story. If you will notice, after my name, I'm a registered professional engineer in the state of Texas. In software, out of 40,000 registered engineers, there are maybe less than 100 of us, because no one requires it. The specialty is SEE. Nobody requires it. And people ask me, why did you go through the rigor of getting your PE license? Parts of it was a little bit of a chip on my shoulder, because people would say to me, well, you code. You're not an engineer. You're not a real engineer. Throughout my career, I worked with civil engineers doing useful service life on mostly Air Force airframes. I worked with industrial engineers to develop systems methodologies. I worked with mechanical engineers on some CAD type systems. I had worked with all these different engineers, and I really felt like, wait, software engineering is an engineering domain. So I got my PE license, and anyone who tells me I'm not an engineer, I show them my card from the state of Texas and say, go argue with the state of Texas. They say I'm an engineer. I guess it was a lot of work and money just to prove a point. But so anyway, software doesn't build itself, and it's by a process. Like any good engineering, it's a process. Waterfall model, spiral model, evolutionary model, whatever the process is, you don't want to have the chaotic model of, hey, let's sit down and just start hacking some code. You know, hey, I think I've got an idea for, so let's just go out and hack some code and see what happens. Sometimes you can do that for fun and games, but you don't want to do that in anything that can be a product or operational model. You see this a lot in apps. Everybody talks about apps being on your phone and apps and this and that. But something like 60% of apps never survived a version 2. You know, now there's some reason for that. They found out they weren't needed. They weren't built robust enough, whatever. Traditionally, security's been an add-on. So what we need to do right now is a sea change. We need to integrate security in the software development lifecycle process requirements. It needs to be in software engineering. It needs to be in every single class where you produce code. You need to have security requirements. Is this real life? No. Will we need to do this? Yes. So we need to learn the use of secure coding methods to prevent opportunities to introduce security failings. I'm not going to go through these. I think I've explained them in the definition. If you've developed software, you know what I'm talking about. Comments, commenting your code, documenting your code. The fun is actually putting your fingers on the keyboard and developing the code. But you have to adhere to the process, and the process is to go through a set of steps, to do what is required of those steps, to produce the artifacts or documents, those steps. And basically it's in needs analysis, requirements, specification, design, coding, testing phases, operational. You know, nothing in my book should ever go operational without being put in a digital sandbox, the like. So secure coding is creating code that does what it's supposed to do and only what it's supposed to do. And so Microsoft developed the Security Development Lifecycle. You have other professional organizations that have now started looking at security as part of that life cycle. So here's what you need to know in the secure coding. You need to minimize attack surface areas. That's a strategy to reduce a place where code can be attacked. This is your OWASP top 10, your SANS top 25 programming errors. Then you need to do threat modeling, which is a process of analyzing threats and their potential effects on software to put in detection and protection mechanisms against threats. So the output of the threat model is a compilation of threats and how they're going to interact with the software. Very important slide. 2 important tools. I want to minimize the attack surface to reduce the places where code can be attacked. That's a risk management issue. And I want to develop a process or use a process of analyzing threats and their potential effects. And I want to build something in my software to detect and protect. So we're going to go through the requirements phase. What do we want this to do? I spent a good part of my life early in my career as a software. At that time, my first title was programmer/systems analyst. I don't know what they are now. But basically, the systems analyst part was sitting down and gathering the requirements for my user base. And sometimes I would have to tell them, your requirements are not good requirements. They are, you're seeing the solution at the end that you want to see. I need to know what you need. And this is an art into itself. I don't know if this is a lost art because it's a people-to-people type phase, but it's about completing the requirements. It's about figuring out what the software needs to do, not what the user wants it to do. I used to say, I need a Ferrari. You know, the user would say, I need something, and it's like, no, you're wanting a Ferrari. What you need is a vehicle that will transport and do this and this and this. You are looking at a solution. Let's figure out what the true requirements are. And so we know this, the cost of adding security at a later time rises exponentially. Just like fixing bugs in a software, the earlier you find those bugs and fix them, the more cost constrained. The latter, you have higher cost. Fixing a bug when it's in development is a lot easier and cheaper than fixing a bug when you have 100,000 established user base, right? The same thing about security. So the development of both functional and non-functional security requirements have to come up in the development of use cases. And it's not in here. It's in my risk assessment, risk management class, but I teach that there are use cases and there are misuse cases. Use cases is how it's going to work. I'm going to go to my ATM, I'm going to enter my login, I'm going to get money out. Now, give me the misuse cases. How can my security be compromised at that ATM? So in other words, use cases are the bright, sunny unicorns and, flowers and everybody's happy. And misuse cases are, tell me what could go wrong. There's a skimmer on that ATM machine. Someone is shoulder surfing. My password has been compromised. There's an interrogator somewhere that's, as I do something, is picking it up. I don't know. So when it says development of use cases, I should have added here to Dr. Conklin's text, development of misuse cases. Okay? Tell me how it's going to be used correctly. Tell me how it can be used incorrectly. Start giving me insight into those requirements. Hey, that's not in your book, so that would be a good final exam question, wouldn't it? To pay those people back who actually listen to my videos. Somebody needs to remind me of that. Okay, the design phase. You're going to minimize the surface attack area. So it runs counter to the way software has been designed. Most designs come, as it says here, incremental accumulation, adding features and functions. With this, is to minimize this, you need to reduce the avenues of attack that attacker. Obviously, it has obvious benefits, and it's a concept that tends to run counter, as it says. So it's kind of an art unto itself. It's proper design. Let's put it that way. Coding without designing is like building a house without using plans. So even on small projects, people think like, oh, I don't know how to design, it's in my head. No, put down the design, because as the scope grows, the complexity and the opportunity of failure grows also. So part of that design phase has to be design security into every aspect of that software. And then, of course, when you do coding, your next phase, when you actually program it, it's a failure to include desired functionality. I need this to run with a certain performance constraint. And when I add the security code onto it, it takes me outside those boundaries. So what's the probability my code's going to be used? Why don't we just not do that functionality? Or we don't know how to do it, or we do it poorly. So this has to be put in, and security requirements have to be checked off. in the same order of other requirements. So that's when you come to testing. And you need to be aware of common weakness enumeration, common vulnerabilities and exposure. As I said, the National Vulnerability Database, NVD. I will put this on a video. If you don't know what this is, the end of video 1, go look at CWE, CVE, the National Vulnerability Database. Become familiar. Even if you are not going to be a first line at the keyboard cyber worker. If you're a mechanical engineer, if you're a business person, you need to be familiar with what is out there. So again, the coding phase, or there's language-specific failures, are sort of vulnerabilities. The coding has to be very rigorous. I don't know if you still do manual code inspection. At one time when I taught software engineering here in the early 90s, this technique came out of, I believe, NASA. It was called a clean room concept, where they did programming. It was kind of crazy. And the programmers couldn't compile their code. They had to visually inspect it for errors. I think that was a short-lived paradigm. It kind of took away the benefit of being a program and watching your, checking your code, why you were in the job in the first place. So again, and then you have static code analyze tools to design code for potential defects. Now, secure software design and secure is one of those areas that is ripe for AI. Artificial intelligence, you can go in, you can take a software system, you can build a rule base, you can do machine learning, you can do whatever AI technique you want to do and check to see if this is done. And so a lot of people are like saying now, secure software coding, why are we teaching it? Well, obviously AI programs do not create themselves. They are created by people who have done knowledge engineering and know what to put in them. So this is an area that we can start using more AI. However, we need the person in the loop. So the CWE, I don't know, it says 750 now. The top 25, I'm going to shoot this in another video or add it to video 2. Remember our comment about least privilege. The developer understand what privileges are needed specifically for an application to execute. So we talked about least privilege in our first lecture. Now we're saying this needs to be implemented and how it will be implemented. And it is at the software level. We can talk about all these great high-level concepts and make them aspirational, but somewhere along the line, somebody has to do the dirty work. And least privilege of one of these is to understand the software's interaction with the operating system and systems resources, as well as the users, and determine what needs to be accessed and what the appropriate level of permission is, and then put that in the design and implementation and check it in the testing. And somehow, where am I? Sorry, I accidentally knocked my list here. Here's where I am. So the cost of failure and darn it, what is going on? The cost of failure is to heed the principle of least privilege is twofold. You have expensive time-consuming access violation errors, and an exploit is found that allows some program to use portions of your code, and we all know where that can lead. Big trouble. Then we have cryptographic failures. And cryptographic failures, you still get programmers who think, hey, I'm a great programmer. Let me just go develop my own cryptographic algorithm because, I got my degree from A&M and I took cryptanalysis and I know this and I know that. No, 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 no. Never. You need a trusted algorithm always, because these algorithms that are out there have been hardened by hundreds, thousands of people. They have been reviewed. So they come from something. It's developing your own or other things like generating a real random number to feed them. But it starts with using what is out there. I'm going to bypass this a little more details than you need, such as storing private keys in areas where they can be recovered by an unauthorized person is the next worry. That's beyond the scope of this class and how you would do that. We talk about language-specific failures. They were developed without regard to secure coding implications. I think we've talked about testing quite a bit. Use cases. Misuse cases, yay, there it is. It is on his slide. Can be formulated to verify that vulnerabilities cannot be exploited. Fuzzy testing uses random inputs. That's what I was saying. They use all different kind of files. Throw this kind of file. Throw an MP4 file. Let's see what happens when you throw it as input. White box testing, black box testing, gray back testing, and then final code should be subject to penetration test. This is one aspect of testing that has to do with security. We are now going to try to figure out how to break it by nefarious means. We're going to close with that because it's been about 25 minutes and I know your eyes are probably glazing over. We still have video 2 to go through. I want you to stop what you're doing now. I want you to go to look at the National Vulnerability Database, and I will include that in the second video. Thanks for sticking with me. Be back with you soon.